Hello everybody, how's everybody doing? CRS here. In this video, we will be talking about frictional force and the direction associated with frictional force in case of rotational dynamics. There is a body that's rolling. Now, if I just told you, that is something we all to an extent assume as well. If somebody asked us what is the direction of friction that would act on a body, we would always say that if the body is moving in the forward direction, friction always acts in the backward direction. Or does it? So this video answers that question. Let's look at the problem statement. What is the direction of frictional force if the radius of gyration of the body is k? So we have a round body out here. It could be a disc, it could be a sphere, it could be anything, a ring, let's say. It doesn't matter what it is right now, but the radius of gyration of the body is k. Depending on the size and shape of the body, we all know that the radius of gyration would change. It is the distance to the effective mass of the body. When that is the situation, this is the point of contact. That's where the point of contact lies. Now, if I apply a force at a distance x above the center of the body, then the frictional force that would act on this body would be at the point of contact. Now, it can only act in two directions. It can either act in the forward direction or it can act in the backward direction. Now, the question that we have to answer is, in what direction does it act? So let's try to figure that out. Rolling motion, dear friends, pure rolling motion, by which I mean that the body isn't slipping, is a combination of pure rotational motion and pure translational motion. So if you put translational motion and rotational motion of the body together, then the body would do rolling motion, right? So let's talk about just pure rotation of the body. Just let's separate out these two things about rolling motion. Let's look at rotational motion separately and translational motion separately. Let's see if we get an idea. At the point of contact, due to rotation, the rotational motion causes an acceleration of this body. If the disc or whatever this round object is trying to spin faster and faster because it's rolling in that direction, there is going to be acceleration of that point in the backward direction due to rotation. So I'll call it AR, right? And due to translation, the body is sort of going forward also. Because of that, the translational acceleration would be in this direction. I write it AT. Now, depending on which of these two accelerations is greater, the tendency of that point in contact would be in the direction of the greater acceleration. So if acceleration due to translational motion is greater than the acceleration due to rotational motion, then this body this point has a tendency to move in the forward direction, but the friction has to stop it. So the friction will act in the backward direction. So if the translational acceleration is greater, then the friction will act in the backward direction. If the rotational acceleration of that point is greater than the translational acceleration, then the friction will have to stop it from going back. Because it's a rough surface, friction will have to act in the forward direction. So there are two possibilities out here. Now let's answer this more mathematically. Now that was a qualitative understanding of the direction of frictional force. Remember, the direction of frictional force is absolutely important when you are solving for let's say the angular velocity of the body after a certain time, or could any question that would involve drawing a free body diagram of a rolling object on a rough surface. But anyway, going further, let's continue. Do you see that now these two accelerations are the ones that determine the direction of friction? The net acceleration of the body of the point of contact, not the body, the point of contact, can simply be written as the difference between translational acceleration of that point and the rotational acceleration of that point. So that's the direction, that would be the acceleration at that point. If at is greater, then the net acceleration will be in that direction. Of course, there is a centripetal acceleration. We are not bothered about that. That does not decide the frictional force as such. But then coming back to here, these two accelerations for that matter. If AT is greater, then friction acts in the backward direction. If AR is greater, then friction acts in the forward direction. Now, the question says the radius of gyration is k. So let's do something with that. Let's only look at the translational part of motion currently. So translation, right? We all know Newton's second law. Force acting on a mass would accelerate it translationally. So I have written F is equal to m into at. So what does the expression for a translational acceleration become? It becomes equal to F divided by m, my dear friends. Now going further, similarly for rotational motion of the body, so there is a rotational motion of the body because of which there is AR, which is the acceleration due to rotation of the point of contact, can also be similarly found. You will have to write down the Newton's second law for rotational dynamics. Just like F is equal to m into at is there, you have tau equal to I alpha, right? This is F equal to m into a for rotational dynamics. Tau is torque, I is moment of inertia, and alpha, my dear friends, is angular acceleration. And this body is pure rolling. So the torque here, I just divide the board. We have tau. Torque is defined as force multiplied by perpendicular distance. Force is here. The axis of rotation is right at the center. From the axis of rotation, the force is at a perpendicular distance x. So I write tau as F into x. The moment of inertia I for any body can be expressed in terms of its radius of gyration. And the radius of gyration, my dear friends, is k. So moment of inertia can be written as mk square. Alpha, because the body is in pure rolling motion, you can write AR divided by R. Just like V is equal to R omega, and V would be equal to omega would be equal to V by R. Similarly, alpha would be equal to A by R because A is equal to R alpha. In place of alpha, I have written AR divided by R. AR is just now said, it's the acceleration of that point of contact due to rotation. Now, what does AR become equal to then? AR, my dear friends, becomes equal to F into R into X divided by mk square. That is AR. Now that we know what is translational acceleration of that point of contact and the acceleration due to rotation of the body, we can put both of these equations in this one, and you will get something fruitful. It would be a shortcut for you to do problems next time. So listen to me carefully. Put this here. Then the acceleration, my dear friends, would simply become equal to at is F divided by m minus AR is FRX divided by m k square. You can pull out F by m as a common factor. You will have 1 minus Rx divided by mk square. I mean, there is no m here, there is just k square. Sorry. So when that is the case, you can take an LCM here. A becomes equal to F divided by m multiplied by k square minus Rx, my dear friends, divided by k square. This is all you will have. Now, when will this answer be positive? Look at this equation. You will have an answer, this answer to be positive, if k square is greater than R into x. R into x. R is radius, x is the distance above the center where a force is being applied. Now this is when our acceleration would be positive. Acceleration being positive would mean that translational acceleration is greater than rotational acceleration. That's when you get acceleration to be positive. So that means translational acceleration is in that direction. The tendency of the point of contact is to move in the forward direction, so friction must act in the backward direction. So we would simply say the friction is in backward direction, right? So that's something you can conclude. And similarly, if k square is less than rx, my dear friends, if k square is less than rx, then what happens? Then the answer turns out to be negative. And the negative answer simply means that the rotational acceleration of that point, acceleration due to rotation, is greater when compared to translational acceleration. So the tendency of that point is to slip in the backward direction, but friction would stop it by acting in the forward direction. So the friction, my friends, would act in the forward direction. So this particular idea is the one that will really save your time in any competitive exam. You try to write it. Okay, so I'll just put that in a box so that you remember it. Okay, just put that in a box, make that box a little bigger. Well, if you can remember this, drawing free body diagrams in rotational dynamics in case of rolling motion will become a cakewalk. Now the other question that would haunt you is, sir, okay, when a force acts above the center, you will have to check this condition to see whether the frictional force acts in the forward or it acts in the backward direction. So what if the force always acts in the up below the center? Then invariably the frictional force will only act in the backward direction, because both translational and rotational motion, rotational accelerations will be pointing in the forward direction. You can see for yourself. This has a tendency to rotate the object like this, but if the same force acted in downward at a point down below the center, then it would have a tendency to rotate it like that. Translation also is taking it forward, so that point will only want to slip in the forward direction. Friction will always act in the backward direction. So that is something that I need you to remember. Let's go further and solve a problem based on this. Well, my dear friends, here we go. The question says a horizontal force F is applied on a disk at some distance x above the center. So let me imagine a disk. That's a disk, my dear friends, right? Here is a disk. Let me mark the center for the disk. We also need to draw the floor. So here we shall draw the floor. So that becomes the floor, right? Okay, that becomes the floor. The question says that at some distance x above the center, let me just draw a horizontal line passing through the center. Maybe this would do the job, something like that. That is the horizontal line passing through the center. We need to apply a force, right? We need to apply a force like this at a distance x above the center, at a distance x above the center, such that it can roll without slipping. The pure roll means without slipping on a smooth surface. That means there is no friction on this surface, but still it will have to roll without the frictional force acting. Now that's the question. Nobody is there to stop the point of contact from slipping now, but you need to apply a force in such a direction, that it at such a height from the center x, so that the body is still able to pure roll. Well, you can make that happen. You can make that happen from the knowledge of previous exercise. If the translation, you apply a force at such a height above the center, so that the translational and rotational accelerations are both equal, then what will happen? Then this point of contact will experience no acceleration. So if it is initially at rest, it will continue to be at rest, but because there is a force acting, it will continue to, it would start rolling. And we know that in rolling motion, the point of contact is always at rest, so you will be able to set it in pure rolling. So that's the idea behind the solution of this question. So the body will pure roll if the translational acceleration is equal to the rotational acceleration for the point of contact. The acceleration due to rotation it is. So that's what it is. In the last case, we have seen that AT is F divided by M, right? You see, AT is F by M and AR is FRX divided by MK square. So this is FRX divided by MK square. You have F by M and F by M getting cancelled, right? You have F by M and F by M getting cancelled. What do you have? Cross multiply. You will have K square equal to Rx, my dear friends. The question says it's a disk, right? It's a disk. If it's a disk, my friends, then the moment of inertia of a disk about an axis passing through the center perpendicular to its plane is mr square by 2. That's the moment of inertia, and that would be equal to mk square. To find the radius of gyration, equate any moment of inertia to mk square. You will see that m gets cancelled. K would be equal to r by root 2 if you take a square root, but here I just need k square, so instead of k square I shall substitute r by 2. So let me do that. When you substitute r square divided by 2, my dear friends, in place of k square, because k square is equal to r square by 2, you will have r into x. R and square gets cancelled. So what does x become equal to? Dear friends, x becomes equal to r by 2. X becomes equal to r by 2, which simply means that if you put the force above the center at a distance equal to r by 2, then this disk will not experience any frictional force, because the acceleration of the point of contact is 0, and because of which this will start pure rolling. Fascinating, isn't it? You don't really need frictional force for making a body roll, pure, to put it in pure rolling motion. So more of this kind in the next video. Keep yourself busy in the preparation for exams that are coming up. You have JEE exam, you have the Neet exam coming up. These concepts will help you by leaps and bounds. I wish you all the best. I'll be back with another video, but do remember, the day you stop growing is the day you start decaying. Thank you so much.